Welcome back to the Deep Dive. So today we're really tearing into the first principles of machine learning.
Yeah, the real basics, getting that foundation right.
Exactly. And we wanted to kick things off with, well, a pretty surprising moment, right? That really threw ML into the public spotlight. 1997.
Ah, Deep Blue, of course.
Deep Blue versus Kasparov.
Yeah.
IBM's machine beats the world chess champion. A huge deal back then.
It's still, the moment everyone points to, but the fascinating part is when you dig into the details of that match.
Right. What was it?
Deep Blue. It was churning through, 200 million chess positions every single second?
200 million. And Kasparov, the best human player alive.
Maybe 5 to 10 positions a second, if that max.
That difference is just staggering. And yet he played almost at its level.
Almost. And that right there, that highlights this core idea. The human mind wasn't just doing brute force calculation. It had some other trick,
Some kind of shortcut. Or intuition. Abstraction, maybe.
Exactly. Something computation hadn't quite nailed yet. And really, the quest to capture that trick up the sleeve, that human intuition, that's kind of the heart of modern machine learning.
Okay, I like that framing. Not just speed, but efficient knowledge.
Precisely.
So if that's the goal, where do we start? As someone trying to get this, as if we're the course doctor explaining chapter 1, what's the mission here?
Good question. The mission for you listening today is really to get the philosophy down, understand the starting points, what learning actually means in this context, and critically, how we figure out which problems ML should even be pointed at.
Because it's everywhere now, isn't it? It's not just chess anymore.
Oh, absolutely. It's recommending toys, suggesting the next book you'll love, predicting stock market trends, even helping doctors spot tumors earlier.
Wow. And optimizing energy grids, too, right, for green earth initiatives.
Yep. It's become this foundational layer for decision-making in, almost every field.
Okay, so let's pull on that historical thread, then. We see it now. But where did this idea of prediction, of machines learning, actually start? You mentioned Kasparov's trick, but the math came first.
Way before. You got to go back even to the 18th century. Think Thomas Bayes.
Bayes' theorem.
The very same. His work back in 1763, it's all about dealing with uncertainty, right? How new info changes what you believe. That philosophical idea underpins so much of probability in ML today.
Okay, handling uncertainty. What about finding the patterns in the noise?
Right. Fast forward to the 19th century, 1805, we get the method of least squares formalized.
Least squares.
Yeah.
Sounds familiar.
It's basically the idea that if you have messy data points, you can find the single best straight line that minimizes the overall error or distance from those points. Super foundational for regression.
Got it. Finding the best fit.
And then jump again, early 20th century, 1913, Andrei Markov. Markov chains, which are all about sequences, predicting the next step based on the current one. Essential stuff.
So the math tools were there for uncertainty, patterns, sequences. But when did it become about intelligence? When did machines start thinking?
That's the big leap, the 1950s. You have Alan Turing. His 1950 paper is legendary. He asked that huge question, can machines think?
The Turing test origin.
Exactly. And he's the one who really proposed, seriously, that machines could actually learn.
And people started building things almost right away.
Pretty much. Arthur Samuel, 1952, he gets a program to play checkers, and it learned. It got better over time.
Wow.
Then, just 5 years later, 1957, Frank Rosenblatt designs the perceptron, the first neural network, trying explicitly to mimic how the human brain might work.
So the seeds were planted early. And if we connect that back to Deep Blue versus AlphaGo.
Yeah, it's a great contrast. Deep Blue, incredible engineering, but mostly brute force search, just calculating millions of moves. AlphaGo, beating the world Go champion decades later. Go is way more complex than chess, more possibilities. AlphaGo didn't just calculate, it learned through experience. Reinforcement learning, specifically. Playing itself, getting feedback.
That's the philosophical win, then. Learning from experience, not just raw power.
That's the essence of it.
Which brings us right to the core question. If we're stripping away the silicon and wires, what is learning? From an ML perspective.
Well, let's start with us. How do humans learn? It's basically, getting info by observing stuff and then using that info to get better at doing things, like improving your homework scores or launching rockets more successfully.
Okay, makes sense.
And the source material does a nice job linking this to 3 ways we learn, which map really well onto ML concept.
Oh, cool. What's the first one?
The most obvious one. Learning with an expert guide. Think of a baby learning words from a parent, or a student learning from a teacher. The expert provides the right answers, the labels.
That sounds like supervised learning.
Okay. Exactly. You jumped ahead, but yes. That's the analogy for supervised learning. The expert gives the labels.
Wait, was number 2?
Second is a bit more subtle. Learning guided by past expert knowledge. It's like using what you already learned in a new situation.
How so?
Imagine you learned colors from a teacher, red, blue, green. Later, you see a box of mixed objects. You can group them by color because of that past knowledge, even if no one's telling you, group these now. Or a marketing pro predicting customer preferences based on rules their old boss taught them. It's transferring knowledge.
Right, applying old lessons. Got it. And the third?
The third is learning by yourself. Pure trial and error. Think of a baby learning to walk. They try, they fall, they adjust. No one's giving them explicit instructions for every muscle movement.
Or an adult learning to drive, maybe.
Perfect example. You figure out what works, rewards smooth driving, and what doesn't, mistakes, jerky stops, through repeated attempts. You build your own checklist.
Okay, so supervised, transferred knowledge, and self-learning. Those analogies are helpful. How does that translate into the formal definition?
Right, the universally accepted one comes from Tom Mitchell. It's elegant, really. A program learns if its performance, P, at some class of tasks, T, improves with experience, E.
PTPE, task, performance, experience. Let's make that solid. Image classification example, like telling cats from dogs.
Okay, great example. The task T is classifying new images it hasn't seen before, assigning the label cat or dog.
Simple enough, the experience.
E. That's the data set it learns from. All the pictures you feed it that already have labels. Thousands of images clearly marked cat, thousands marked dog. That's its experience.
And performance P is how well it does.
Exactly. It's the metric. Usually the percentage of new unlabeled images it gets right. If you give it more experience, more labeled images, and its accuracy goes up, its P has improved. Therefore, it has learned.
Okay, TPE, clear. So how does the machine actually do that? How does it go from seeing thousands of cat pictures to correctly identifying a new cat picture, improving P? It can't just memorize them all.
No, memorization isn't learning. That's like cramming for a test and forgetting it all the next day, right?
Right.
The machine has to go through a process. Think of it in 3 stages. Data input, then abstraction, then generalization.
Okay. Data input is just feeding it the experience, the labeled data.
Right. But the crucial step, the magic, if you will, is abstraction. This is where it stops being a parrot.
It needs to build that conceptual map you mentioned.
Precisely, like how we learn about animals. We don't memorize every single feature of every dog we see. We abstract. We form concepts. 4 legs, fur, barks, that's a dog. Scales, cold-blooded, probably a reptile. This summarized representation, this map based on key features, that's the model in machine learning.
Ah, the model. So the model isn't the data itself, it's the distilled knowledge from the data.
Exactly. It could be a set of if-then rules, a mathematical equation, some complex data structure. Depends on the technique.
And getting that model right, that's training.
Yes. Training, or fitting, is the process of tuning that model, whatever form it takes, so it best reflects the patterns in your specific input data, your training data.
So if the model is, say, a simple line equation like y equals c1 plus c2x,
then training means finding the best values for those coefficients, C1 and C2, so that the line fits your training data points as closely as possible.
okay, makes sense. But then comes the hard part, generalization.
The ultimate test. The model was trained on a finite set of data. Now it has to work on new unknown data, the test data.
Why is that so tricky?
Well, a couple of reasons. One, the model might have gotten too good at fitting the training data, including its quirks and noise. It overlearned the specifics and can't see the general pattern anymore, overfitting. Or the new data might just have characteristics the training data never showed it, so the model makes mistakes. Because it has to generalize from incomplete information, ML models inherently operate on an approximate or heuristic basis.
A heuristic.
Yeah.
Like a rule of thumb, not a perfect law.
Exactly. It's a best guess approach based on the patterns it learned. It's powerful, but it's not perfect knowledge. It carries a risk of error, just like human gut feelings.
Got it. So this process data, abstraction, generalization underlies everything. Now let's break down the main types of ML based on how they learn. You mentioned supervised earlier.
Right. Supervised learning is probably the most common. The key, again, labeled training data. The machine learns a mapping from inputs to outputs because you gave it the correct outputs for the training examples.
And its goal is prediction, essentially.
Primarily prediction. And it splits into 2 main types. First, Classification.
Predicting a category.
Exactly. Is this email spam or not spam? Is this transaction fraud or not fraud? Is this tumor malignant or benign? The output is a discrete class label.
Okay. And the other type of supervised learning?
Regression. Here, you're not predicting a category, but a continuous real value.
Like a number.
Precisely. Predicting the price of a house tomorrow. Predicting the temperature next Tuesday. Predicting sales figures for next quarter. You're fitting a line or curve to predict a specific numerical outcome. That least squares method we talked about. Classic regression technique.
Okay, supervised. Labeled data prediction, either classification or regression. What's next?
The flip side, unsupervised learning. Think descriptive, not predictive. Here's the big difference. No labeled training data.
No labels. So what's it trying to do?
It's trying to find inherent structure, patterns, or groupings within the data all by itself. Pattern discovery.
Does it do that?
The main technique here is clustering. Grouping similar data points together based on some measure of similarity, like distance. Think customer segmentation. You have data on customer purchases, demographics, etc., but no predefined types. Clustering algorithms try to find natural groups of similar customers.
Finding tribes in the data.
Good way to put it. And related to that is association analysis. This is about finding rules that describe relationships between data items.
Like the classic supermarket example.
Exactly. Market basket analysis. Discovering that customers who buy, say, diapers and beer together often also buy chips. That kind of pattern discovery is gold for things like store layout or targeted promotions.
Okay, unsupervised. No labels. Finding structure, clustering, and association. What's the third main category?
Reinforcement learning, RL. This one is quite different. It's about learning to make a sequence of decisions by trying things out and learning from the consequences.
Like the baby learning to walk analogy.
Precisely. It's learning autonomously through rewards and penalties or mistakes. An agent, the learner, operates in an environment. It takes actions. If an action leads closer to its goal, it gets a reward. If it doesn't, maybe it gets nothing, or a penalty.
So it learns a strategy, a policy over time.
Exactly. It learns what actions to take in what situations to maximize its total reward. We mentioned AlphaGo using RL, a more everyday example, self-driving cars. The car, the agent, is in the environment. Traffic, roads, weather. It takes actions, accelerate, brake, turn. It gets feedback positive if it makes progress safely, negative if it does something risky. It learns the optimal driving policy through this interaction.
That really highlights the difference from Deep Blue's approach again. It's not just programmed rules, it's learning from dynamic feedback.
Absolutely. Deep Blue was search. AlphaGo and RL in general is about learning through experience and reward. Big difference.
Okay, so we have the three main paradigms: supervised, unsupervised, reinforcement. Now, if you're actually going to use ML, how do you approach a problem? The source mentioned a framework for a well-posed problem.
Yes, this is crucial. You can't just throw ML at everything. It's about being systematic. 3 key questions you have to answer first.
Question 1.
Step 1. What is the problem, formally? Define T, P, and E. Task, performance, experience. Let's say you want to build an autocomplete for emails. T, suggesting the next word. E is a massive corpus of emails to learn from. P, the percentage of times it suggests the correct next word. If you can't clearly define these 3, you don't have an ML problem yet.
Okay, nail down T, P, E, step 2.
Step 2, why does this problem need solving? What's the motivation, the benefit? Is it solving a major business need like fraud detection? Or is it, a nice-to-have feature like movie recommendations? Understanding the why helps justify the effort and resources.
Makes sense. And step 3.
Step 3, how would I solve this problem manually? This sounds counterintuitive, but it's vital. Before you automate, think through the human process. What rules, what knowledge, what steps would you take? This helps unearth the domain knowledge the machine needs to eventually learn or abstract.
So, define TPE, justify the why, and understand the manual process first. Good checklist. What about when not to use ML?
Also critical. Don't use ML if humans are already excellent and fast at the task, or if it needs constant human oversight, think air traffic control. You don't want a probabilistic system there.
Right.
Also, avoid it for really simple deterministic tasks. If you just need a price calculator based on fixed rules, write a simple program with if-then statements. ML is overkill and might even be worse.
And the biggest don't.
Data. If you don't have enough good quality training data, just stop. Don't even try. Bad data, or too little data, leads to models that are useless at best and dangerously misleading at worst. The impact of bad data is way worse than you might think. Garbage in, garbage out. exponentially so.
Okay, that's a strong warning. Finally, there's the ethical dimension, the fine print. Privacy seems like the big one.
It's huge, and it's often the biggest hurdle to actually deploying an ML solution.
Ah,
The models learn from data, often personal data. The insights they uncover, like predicting someone's shopping habits or maybe even health conditions based on subtle patterns, can feel deeply private.
and if those insights are used carelessly,
People get upset, understandably. Think targeted ads that feel too specific, revealing something you didn't want known, or worse, leading to discriminatory outcomes. This can cause real harm and lead to legal trouble.
so the takeaway isn't just build good models,
It's that proper human judgment is absolutely essential before acting on any ML output. The algorithm provides a prediction or an insight. Humans must decide how, or even whether, to use it responsibly. The responsibility doesn't stop at the code.
that's a really important point to end on regarding the process. Okay, let's quickly summarize the key takeaways from this first dive.
Sure, we saw ML's roots are deep in math and philosophy, trying to capture that human learning essence. The core process is data input, abstraction, building a model, generalization, applying it.
And the three main types are supervised, uses labels for prediction, classification, regression; unsupervised, no labels, finds patterns, clustering, dissociation; and reinforcement learning, learns via rewards mistakes.
And for anyone wanting to start coding this stuff, the main tools you'll hear about are Python, especially with libraries like scikit-learn, R for statistical focus, and then the commercial platforms like MATLAB and SAS are still widely used in industry.
Perfect. So here's a final thought to leave you with. We started with Deep Blue using brute force search, while modern systems like AlphaGo use reinforcement learning, learning from experience and reward.
Right, a clear evolution.
If machines are getting so good at learning from experience, what's the next frontier? What part of that Kasparov trick, that intuition, that ability to find the right path without searching billions of options, is still fundamentally human? How much of that efficient, almost gut-level intuition is left for us to figure out how to automate?
That's the multi-million-dollar question, isn't it? How do you teach a machine true intuition? We're getting closer, but maybe there's still something uniquely human there. Food for thought.